Hello everybody and welcome back to more of the 2000 Cayley paper. We're on to question number 17. Okay, so what does question 17 say? In the regular hexagon A, B, C, D, E, F, two of the diagonals FC and BD intersect at G. Okay. The ratio of the area of the quadrilateral FEDG to BCG is, okay, so what can we see about these diagonals? So FC cuts straight across, it's going to be parallel to AB and ED. And looks like it's going to be a right angle at G. And we have this tiny little triangle here compared to this little triangle here. Well, what if we cut off this slice? Then we have a copy of BGC. And we just need to figure out BGC compared with the resulting EDG whatever quadrilateral. Okay. I think it's time to draw a picture and see what we can see. So, let's draw ourselves a little copy of the hexagon. That's not the most regular hexagon, but it'll do. Okay, and we have A, B, C, D, E, F. And these points up, and we have G. Okay. So, we want to compare this area to this area. Okay. Alright, so let's try and figure some things out. First of all, since it's a regular hexagon, we know that all of these side lengths are the same. Okay. And we also know that each of these interior angles is 120. I don't know which of these I'll need, but we'll mark them all. Okay. So, what can we see here? Well, FC cuts the whole thing in half. So, what have we got here? So, angle BCG is equal to angle DCG. And those are going to be equal to a half of this angle, so a half of the 120, so 60 degrees. So each of these in here is 60 degrees. Okay. We can also see that BC and CD are the same, as indeed are all the side lengths of the hexagon. So BCD is isosceles. I can never tell if I'm spelling that right. I think there's another S, isosceles. You would think after so many years in math I would know how to spell that word. No, see, the S doesn't look right there either. I'm going to switch it back to the way it was. Maybe I think I was right the first time. Okay. So if that's the case, then each of these two angles, GBC and GDC, are equal. and it's not hard to see that they're going to be 30 degrees. We have to have a total of 180. We already have 120 accounted for, the angle at C here. So that leaves 60 left over to split evenly between the two of them, so we're going to get 30 degrees. Okay. So BGC, sorry, is the 180 degrees for a full triangle, minus the 60 degrees for BCG, minus the 30 degrees for GBC. So we do indeed get a right angle here. And we also have that DGC equals 90 as well. The exact same reasoning applies. So we get a nice bright right angle here. But what's more, BGC is a 30, 60, 90 triangle. So it's a triangle whose interior angles are 30, 60, and 90. And that means that there is a ratio between the sides. So your general 30, 60, 90 triangle looks like this. You have a side length of 1 on the shortest leg, the leg opposite 30. And then the hypotenuse is going to be 2, and the height is going to be square root of 3. This is what all 30, 60, 90 triangles look like. And they really do, they come up a lot on contests, so it's one of the sort of triangles I recommend people be very familiar with. You can show this just by knowing a little bit about trig, knowing what the sine of 30 degrees and the cosine of 30 degrees are. You can come up with this triangle. But it comes up a lot, other than sort of the integer Pythagorean triples, so like 3, 4, 5, 6, 8, 10, 5, 12, 13. This sort of right angle triangle comes up the most. Other than those, it comes up the most. So very, very, very important to be aware of 30, 60, 90 triangles, be on the lookout for 30, 60, 90 triangles, and to know what the side lengths are going to look like. Now these are ratios. So if I have a side length of r on the shortest side, then it'll be root 3r and 2r on the other sides, the hypotenuse and the height. So this is what your general 30, 60, 90 triangle looks like. And, you know, if that helps, that helps. If not, maybe it's just because they use the hexagon, we get this nice little construction. But we do see it's a 30, 60, 90 triangle. Now, we have paid a lot of attention to this triangle. We figured some stuff out about it. How about we take a look at the quadrilateral? Now, as I said in the intro, I think what we could do is we could write in AF and create a point H here. Okay. So if we drop this perpendicular, or not this perpendicular, this diagonal here, it's going to hit FC at H, and by the exact same work that we just did to show things about BGC, we're going to see that, EHF is right angled at H, and it's going to have a 60 degrees and a 30 degrees, and they have the same side length, so we can see pretty quickly that these two triangles are going to be congruent. So what I think I can do is I can break this remaining, it's not going to be a square, but it will be a rectangle, into copies of BGC. And then we'll get some integer number of copies of BGC compared with just one. Okay. So, how best to split it up? Well, let's give a name to the side length. So once we have the side length called S, we can put that in here and here and up here. We get some information. Thanks to our 30, 60, 90 triangle, we know that length GC is going to be 1/2 of S. And the height BG is √3 over 2S. Okay? And yeah, if you didn't have your 30, 60, 90 triangle memorized, that's okay. Knowing that you have the angles 30 and 60 in there, you could just use trigonometry. That's okay. It's the 10th grade level contest, so trigonometry is certainly fair game, although I find it doesn't come up that often. So then GC and FH are equal, and they have length S2. They're equal because the two triangles are congruent, so we'll do both of them at the same time. And what was it? BG EH is √3 over 2S. That way I don't need to know what the side length is. It's just S. But I can figure out ratios of side lengths, and that will certainly help me figure out ratios of these areas. Okay. Now, if I were to take the green, so I have a side length here of S, and I have a height of √3 over 2S. If I were to find the midpoint here, I would get S by 2, S by 2, S by 2, S by 2, and all of these triangles are going to have a height of √3 over 2S. So let's give the names to these. One midpoint and two midpoints, M and N. So M was the top midpoint, so the midpoint of HG and ED, respectively. So then what can we see? Well, we can see that EN is equal to ND is equal to MG is equal to HM is equal to S by 2. And what do we have? EH is equal to MN is equal to what have we got here? What was the other one? It was GD. √3 over 2S. And so then we can see that BGC is similar, or is congruent to EHF, is congruent to EHM, congruent to NMH, which is congruent to NMG, which is congruent to, what was the last one? GDN. So 5 of these triangles make up the quadrilateral we're talking about. So EDGF five copies of triangle BGC to one copy of triangle BGC. It's 5-1, and that is E. All right. Okay, that's a nice little question. We didn't have to do a whole lot. I was worried when I saw this 3 root 3 and this 2 root 3 that this could get a little complicated, but it was rather nice. This quadrilateral split up into a nice integer number of copies of this triangle, so I think overall pretty good. I can't wait to see question number 18, and if you'd like to see question 18, join me in the next video.